class that I was going to do electrochemistry, but I didn't realize we only had 4 classes left, so I'm going to skip electrochemistry and go straight into kinetics, which was what we'll be on for the rest of the class. Well, I'm just going to write kinetics up here. I don't know why. There's really no point, but just to keep us reminded what we're talking about. The thing. So what we've been talking about again is equilibrium, right? We said that by measuring delta G for a process, for let's say for a reaction, a chemical reaction. We can predict which direction the reaction will go. Right, and we know the rules here. Right, if delta G is less than 0, this means that the equilibrium constant is greater than 1, which means it's product favored. Right, I don't have to remind you of these, but you'll just have it anyway. Delta G is greater than 0, then K is less than 1, which means we have a reactant favored system. And of course, if delta G is equal to 0, K is equal to 1. And it's in equilibrium. Equally balanced between the two. Okay, but the thing where you can think of any old reaction, we can calculate delta G for it, right? That's the whole point of this homework 5. We'll be doing exactly this. Measuring how things are product favored, reactant favored. But what this doesn't tell you is how long does it take to reach equilibrium? I don't have anything about a time scale. And that could be a problem because there are many product favored reactions. For instance, certain transferring electrons from one species to another, redox reactions, oxidation reactions, right? Where the reaction that's occurring is you're moving electrons formally from one species to another. Those tend to take very short amount of time. Electron transfers are usually on the order of 10 to the minus 15 seconds. Those are really fast. The rates are incredibly fast. But there are plenty of reactions that are product favored that take hundreds of thousands of years to complete. And these are conditional reasons, like for instance the reactions that occur in the interstellar medium. If you're in seminar right now, you've seen plenty of these strange reactions that occur in space that are delta G less than 0, very clearly less than 0, very product favored reactions. But the system doesn't. But in the interstellar medium, the system doesn't reach equilibrium, if it does at all, for hundreds of thousands, even millions of years, right? So there's a question then of, well, just because a reaction is feasible energetically, right, that we form products, doesn't mean that it actually is efficient. Right? So the question is of efficiency. And so that's what kinetics is about, right? Kinetics is about how do we use thermodynamics to measure how long something takes. Right? So we're going to tackle it with the same tools that we've used before. Things like energy differences, right? Thermodynamics, delta G. We're going to use the same tools we are, but we're going to instead look at a process a little more carefully and realize that the energies that we care about in terms of what determines how fast something goes are different than the ones that determine equilibrium. Right? We have to look for a different type of energy change. Delta G of the reaction only tells us which way it's going to go. It doesn't really, but there is another term that we can calculate or measure that allows to tell us how fast it goes. And that's kind of where I want to get to today. So what I'm going to do over the next 4 lectures, we're going to introduce what it means to measure kinetics. What is the kinetic model that we can use for chemical reactions? And then we'll go through examples. Basically, the next 3 lectures after today will be different examples. We're going to look at some classic examples. And I'll just kind of summarize them. One are unimolecular reactions. This is where you take a single molecule and it does something to itself to form new products, right? These are the idea of taking a molecule A, and it gets converted into products. Right? These are very interesting reactions, and even though they seem quite simple, they're actually, the physics of them are very interesting and quite subtle. And we'll also look at bimolecular reactions. In fact, we'll start with an example that's a bimolecular reaction. That's the A plus B. Right? Two different molecules collide, or they could be the same as well, to form products. And then we'll also look at some other types of cases, what we'll call zeroth order reactions. These are reactions that have fixed kinetics. They have the same rate no matter the conditions. And we'll also look at catalysis, right? The presence of a catalyst and how that affects kinetics. And we'll look at two cases. One, we'll look at what's called homogeneous catalysis. Homogeneous means that the catalyst is in the same phase as the substrate, so the reactants, the catalyst in the same phase of reactants. And the example we're going to use is enzymes. Right? We'll look at enzymes, right? Biological catalysts. And then we'll also look at heterogeneous catalysis, which is where the catalyst is in a different phase than the reactants. And the case we're going to use that we're going to look at is, for instance, the Haber-Bosch process. I kind of talked, when we talked about Haber-Bosch in terms of the equilibrium, I said that we use a catalyst, they use a catalyst to make this reaction go faster and more efficiently. And we'll look at the mechanism and the kinetics of this case and how heterogeneous catalysis will help us. Okay, and so I think, so we'll work on all of this. And what we're going to look at is, we're going to look at it from two different perspectives. We're going to look at, well, some of these. But there's two different perspectives to kinetics. And we're going to kind of switch between them. One is a macroscopic perspective, macroscopic view, which means measure kinetics in terms of concentrations of reactants. Right? We have a system in a volume with some number of moles, so we have concentration. And we'll look at how kinetics changes as we change concentration and temperature. Right? Macroscopic properties of the system. This is kind of the classic way we do kinetics. And the way that's unique to this class is we're going to look at kinetics microscopically as well, which is measure kinetics on a single molecule basis. We're going to look at collisions, for instance. Right? So we're going to look at, and I think next class or the class after, we'll look at what we call collisional dynamics. Right? In order for two molecules to react with each other, they have to collide. So we'll have to think about collisions. And that's what I mean by macroscopic. So instead of thinking about just concentrations, right, we know how much we put in and we can measure how fast the system reacts. We're going to look at it, we have one molecule of A, one molecule of B, and they collide, what happens? And what are the physics of that? And of course, the microscopic goes straight into the macroscopic, right? Everything that we define microscopically can be defined macroscopically. You know, there are two answers to the same thing. It's just one we zoom in further than the other. So I'm going to kind of go in between these, jump around, but we'll spend a lot of time in the microscopic scale because there's some really, really beautiful work that's been done in this field. And in fact, that's kind of how we'll define kinetics today, is microscopically. Well, we'll actually use a little bit of both. So my motivating example today, to define how do we measure the kinetics of a reaction, let's just take a reaction example, a really kind of classic example. Well, here's our motivating example. And the motivating example we'll use is the SN2 reaction of taking CH3Br, treating it with hydroxide ion to to generate methanol and bromine ion. Okay. We use this reaction. Right, we'll think about the kinetics of this reaction. So, but the first thing we should do is think about the energetics of this reaction. Right? What is delta G here? What sign does delta G have? So let's actually call this an equilibrium, right? We might want to call this equilibrium. And the nice thing about SN2 reactions is that we don't even have to do any calculations to predict which way this reaction goes, whether delta G is positive or negative. So I'm going to throw it out to you guys. Let's see if anyone knows. Is this a product favored or a reactant favored reaction? Digging way back into your organic chemistry knowledge, if you have any, if you remember anything. Is this product or reactant favored? What was the product? Why?
I don't know. I did 50-50 shots.
Oh, okay. Well, I'm looking for why too. That's correct though. It is product favored, but the question is, why is it product favored?
Isn't it because the CH3 wants to bond with the OH more than it wants to bond with the bromine?
Why?
Because of the polar, what's it called?
Electronegativity?
Yeah.
Oh, electronegativity. Well, that could be a reasonable way to do it. And maybe we could argue it that way. The way that we typically argue is that so delta G is less than 0 here because, and this is kind of the classic argument, I think you could argue in terms of electronegativity as well, because bromine is a better leaving group than OH. Because it's a weaker acid, or weaker base. So just as a reminder, SN2 reactions prefer leaving groups with the weakest conjugate acid, or sorry, the strongest conjugate acid. Right, so what are the conjugate acids for Br and OH? Well, OH, if you add a hydroxyl ion, you just get water. Of course, we know what the pKa of that is. It's 7 by definition. And Br minus with HBr gives you HBr, and that has a pKa of, I don't know what it is, -3 or something. It's pretty low. Right, so they're like 10 orders of magnitude difference. So this is a stronger acid, which means this is a weaker base, and so that means it's a better leaving group. Right? The better leaving group is the weaker base. Right? So delta G is less than 0 here. I'm going to put a question mark here because I don't actually know what it is, but it's far less than 1, or far less than 7. Okay, so we know which way this reaction goes. All right, but we don't know how long it's going to take. And what I want to use is as a motivating example to come up with a model for us to figure out, well, what do we need to measure in order to measure the kinetics of this reaction. Okay, and so I'm going to use a reaction coordinate diagram to allow us to think about this. So let's draw a nice diagram. I've got some new pens to try here. The door has its own, or a ghost, so it has its own personality. So here's our reaction coordinate, and we'll measure it versus delta G. Right. And we know that the reactants are higher in energy in delta G than the products, so we'll draw the products here, or the reactants here. And we'll draw the reactants, or the products here, a little lower in energy. Let's put them right here, yeah. We don't really know the relative energies of these. We can certainly calculate them. We could just look them up on NIST if we really wanted to, but it doesn't matter for this argument. We're not doing anything quantitative here. Okay, and then we need to think about so remember the reaction coordinate is some motion, right? As you move along the coordinate, some motion is occurring in the molecule. And so let's think about what that coordinate looks like. And all we're doing is we're plucking a Br off and sticking an OH on. So what we can define is that as we go this way, that this is increasing CBr bond length. And then the opposite direction is increasing COH bond length. Okay, and so what's happening is that the OH is coming in and the BR is leaving, right? And so that's what this tracks, okay? We don't have to specify anything more extreme than that for this qualitative example. But let's think about how does the energy of CH3Br, CH3OH change as a function of these bond lengths, right? As these coordinates move, how does the energy change? Right, and I want to introduce a very simple model that if you take this class next semester, you're going to see so much you're going to get sick of it. We're going to let's put it over here. We can model, there's a really useful model for a bond. We call it the Morse potential. Trying these glassboard markers, seeing if they work any better than the Expos. So the Morse potential is a function, it's the energy. So actually, let me define it. So let's say we have a molecule. We're looking at the bond between A and X, for this bond, and let's define the distance between A and X as R. So the bond length, and the energy of this bond, so E of R. Oh, let's also define one more thing. I'm sorry, guys. Let's also define that if you just leave the molecule alone, the equilibrium bond length is R equals R sub E. Okay, if you don't stretch the bond, you don't do anything, it just sits at R sub E. Okay, that's just the default length of this bond. So E of R is this number D sub E. I'll define it in just a minute. And let me make sure I get the order right. It's 1 minus e to the alpha. I'll define alpha in a second. R minus RE, all squared. All right? And D sub E is what's called the dissociation energy of the bond. All right? It's the bond strength. Right? It has units of energy. We call this the bond strength, or the dissociation energy of the bond. And alpha, it's hard to explain without a picture, but I'll draw it in a minute and you'll see what alpha is. It's kind of the shallowness or sharpness of the potential energy, of the potential. I'll explain what that means in a second. And R sub E is the equilibrium bond length. Okay, and so if I were to plot this, you'll see that it looks a lot like the Lennard-Jones potential that we talked about a long time ago. Well, here's E, and here's R. And that, just like in the Lennard-Jones potential, when the atoms are really close to each other, the energy is very high because the atoms repel each other. Right? But as they start to go away, the energy decreases until you reach an equilibrium bond length, where the energy is minimum. And then as you go to infinity, as you stretch them, the energy starts to level out, right? Just like the Lennard-Jones potential. And so just to define the constants, D sub E is the distance between the minimum of the potential and the dissociation limit. R sub E is the value of the bond length right there at the minimum. And the width of this potential is proportional to 1 over alpha. Okay, so as alpha gets bigger, the potential gets more narrow, more sharp. Right? So I'll just kind of sketch them really quick just to show you. So small alpha means that the bond is very shallow. So it would look like this. And then large alpha would be a very narrow and sharply defined bond. It looks kind of like this. Right, something like that. Right, so alpha defines how wide. The term we use for that is how harmonic it is. Right? But we haven't really learned what I mean by that yet. We will next semester. But that value becomes more useful. For us, it doesn't matter. What matters is that we can model the energy of, say, the CBr bond or the COH bonds as a function of its distance, and we can see how the energy changes. Okay, and it looks just like the Lennard-Jones potential. There's a reason why remember the Lennard-Jones potential was this 1 over r to the 12 minus 1 over r to the 6 function. It looks very similar to this, and there's actually a specific mathematical reason why for bonds we use a different one. We'll explain why that is. It's not important right now, but you might wonder why don't we just use the Lennard-Jones potential, but there's actually a really good mathematical reason why we don't. So there's a different one for these covalent bonds, and they're quite similar. So we can define this for any bond we want. We're not going to do that for these bonds, but I just want to know what the energy looks like as we start to move across this reaction coordinate. So let's start with the reactants. So again, if the reaction's just started, the energy's right there. And as we increase the bond length, it means we start to increase the energy, right? We start here at the minimum. That's where the molecule wants to be at. The system always at equilibrium wants to be at the energetic minimum. So the energy increases as we move the bond. So I'll draw it here. Okay, and then it starts to level off. And then there's a really high curve right there, like that. Okay. Correspondingly, we can do the same thing for the COH bond on the other side of the coordinate. But of course, it's going to go the opposite direction, right? Because it's this way. Something like that. So what happens as we go across this reaction coordinate? Well, because we have to break a bond in order for this reaction to occur, the energy increases. But eventually you start to form the COH bond as the bromine leaves, and you lose the energy again. Right? And so we'll see that there's this important region right here where energy is maximum. Energy reaches a maximum here, in between. Okay, you can see they don't connect. Of course, in reality, they have to be continuous. I haven't proven that. But any sort of reaction coordinate has to be continuous. So these actually should meet each other at some point. And so if we just connect the lines, or if we do this, if we actually go in and calculate this reaction coordinate on a computer, what you'll find is something that looks like this. So here's our reactants, here's our products, and the energy increases, decreases, then increases, and then decreases to the minimum, like this. So here's our CH3Br plus OH minus, and our CH3OH plus Br minus. And of course this is a coordinate, and we'll just call it energy for now. Don't worry about G or whatever. It doesn't matter in this case. Okay, so what does the system look like right here at the energetic maximum? Well, if you were to calculate it, you'll find that you get a system that looks a bit like this. Where the OH is starting to, COH bond is starting to form, and the bromine bond is starting to break. Right? Kind of halfway in between, if you will. Right? The energetic maximum between Man, I really hate how much that squeaks. Sorry, I'm going to change colors here. Between two minima is called a transition state. Right, so this is what's called a transition state. We typically notate transition states with a double dagger. And we can call the energy of that, let's think about what the energetic difference between the reactants and the transition state. Right, we call this the activation barrier, E sub A. Where E sub A, we also, sometimes the book calls it delta G double dagger. If you see double dagger, think transition state. It's the activation barrier, or the energetic barrier, excuse me. Energetic activation barrier between the reactants and the transition state. Okay, not every reaction has a transition state, but many do. Okay, in fact, most reactions have a transition state. Okay, so let me call this EA or delta G double dagger. Right. So, in order for methyl bromide to react to form methanol, it needs to have enough energy to get over this barrier. Right. So let's imagine that we have a ball on the surface, right? And if the system is, say, sitting here, what happens? Well, it's just going to roll backwards, right? The energy curvature just tells you it's going to roll backwards. You don't have enough energy to get over that hill. Right? But what happens if I am here? Well, I can roll either way. Right? If I'm at the transition state, this is a metastable state. Right? The system, if you poke it either way, it's going to fall into either of the spot of the plate of either of the wells. Right? So it could go here, it could go here. Now, what if I put the energy of my system up really high? Like here. Well, then it's going to fall into the lowest it can get over the barrier, no problem. If the energy is this high, it can get over the barrier, no problem, and it's going to want to go to the place with that's easiest for it to go. So it can, if it's all the way up here, it's probably it has enough energy to get over. Right? So a molecule up here in energy will be able to cross the barrier and roll over. Right. So what that means is that in order for a methyl bromide to react to a methanol, it needs to have enough energy to get over the activation barrier. Okay, so the criteria for a reaction is that the energy of a molecule of let's say CH3Br plus OH must be greater than or equal to the activation barrier. Okay, so we can draw that. So the idea is that any molecule above this blue line can react, and here can't react, right? Because if it sounds like they're watching the game.
It might be.
I wish I was watching it actually. If anyone's got it and someone scores, let me know.
It's still 1-0.
Okay, that's all that matters to me.
He's like, I don't care if you're paying attention to my class. Let me know the score.
That's right. I watched football in my organic chemistry class like the entire year, so I understand.
I watched elementary.
Okay, so yeah, so the idea is the energy has to be enough. Okay, so we luckily have an equation to allow us to figure out how many molecules are actually have a sufficient amount of energy. Okay, so let's set the temperature to our system to T. So let's say RT is here. Right, this is the thermal energy of the system. Right, so on average, the molecules kind of have this. So set T as temp. So the energy, the average energy of a molecule is kind of on the order of RT. Okay. We're going to feed some thermal energy into our system, right? RT might be above or below the activation barrier, right? Imagine if, the nice thing is that we can really crank up temperature if we want, and then on average all the molecules have more energy than the activation barrier, so of course it'll be very efficient. But we don't know that, we have to keep it general. Right? And the fraction of molecules with energy equal to some value, let's just say EK, is equal to, is proportional to, let's say proportional to, e to the minus EK over RT, right? Boltzmann's equation. This is just Boltzmann's equation. Right? So we're assuming statistical, we're assuming thermodynamic equilibrium. So everything's statistical. Which all means is that we can model the energy of a system by using Boltzmann's equation, right? This E term. Okay. So that means then that the fraction of molecules where energy is greater than or equal to EA is going to be the integral from E sub A to infinity, right? The sum over all the particles that have energy greater than or equal to EA of our fractional term, dE. And of course the exponent, the integral of an exponent is just the exponent. So this ends up being 1 over RT e to the minus EA over RT. Okay. So that means then that the number of molecules in our system that can react is proportional to 1 over RT e to the minus EA over RT. Okay, so now this doesn't have any time in it, right? This has, in fact, this has units of roughly 1 over energy. Right? So this is not a time component. It's not telling us anything about time. But we know if you now have a system where an OH and a CH3Br come and meet, we know how many of those potentially reactive species have enough energy to react. Okay? So we haven't gotten time yet. So we have to include time somewhere. So we haven't been able, soon we'll be able to derive this from first principles, but we don't really quite have that luxury yet. So what we're going to do is we're going to assume that our system has the opportunity to react A times per second. All right, so on average, you could say if this requires a collision, then A collisions happen per second. Okay? And what we can write is that the rate constant, this is the rate constant, is equal to A, right, which is the number of times it can collide. Right, so it's the number of collisions or possible collisions per second times the molecules that can react when they collide. Okay, so this has the right units that we want. We have to figure out the units of A eventually, but we don't have to worry about that right now. Let's set A prime equal to A over RT, just to get rid of it. And KR is equal to A prime e to the minus EA over RT. Okay, so let's see. The rate constant is the number of possibilities or number of opportunities to react times the fraction of the molecules that can react energetically. Right? So let me just write that down just to remind you. This is number of reaction opportunities and this is number of energetically available particles to react. Now, unfortunately, we don't really know how to define A here. Right? We don't really have a prescription for it yet, but we will come up with a prescription for how to calculate A. Right? We have to actually do it in a microscopic way, but we haven't quite gotten there yet. But we can measure it. So, but in fact, when you go do kinetics, right? If we go do this in the lab, you're never going to measure and predict A. A, and in fact, is somewhat of an experimental or empirical number. And the reason why is this. Let's say we go into the lab and do this reaction. Okay, what I'm going to do is I'm going to turn on my spectrometer, and as a function of time, I'm going to monitor the formation of my products. Right? I'm not sure how I'm going to do this. You can do it any number of ways, but and let's say I set it to room temperature, and I monitor it, and it looks like that. All right, so let's say this is T equals 298. Right, the rate of this reaction, we can estimate. Let me get another color. We can estimate the rate by taking the slope of the reaction curve. Right there. The slope is proportional to Kr. It's the rate of formation. How many moles per second are formed, or concentration, whatever the units you're using. All right, then I'm going to increase the temperature. Right? So let's go up to T equals 400 to 320 Kelvin or something like that. And what we find is that the reaction occurs a little more quickly. Right? The slope is higher. 320 Kelvin, we write this down a little lower. And then we heat it up to T equals 400 Kelvin. Look at that pink. And of course, it occurs even quicker. Right? The rate is increasing as we go up in temperature. Right, so then what I want to think about is, okay, well that means that the rate has a dependence on T. Right? The only thing we're changing here is temperature. Right? So let's think about how does Kr relate to temperature. Well, we got T here, we got Kr here. T's an exponent. So let's do some math. Let's take the log of both sides. The log of the rate constant is the log of A e to the minus EA over RT. Which means, and I'll just use some log rules, that means it's the log of A. And then the log of an exponent is just the exponent. So it would be minus EA over RT. Right? And then I'm just going to rearrange this a little bit. And if Kr is equal to minus EA over R times the quantity 1 over T plus the log of A. This is what's called the Arrhenius equation. And the nice thing is that for a reaction that has an activation energy, where everything's normal, everything's statistical, or in thermodynamic equilibrium, the log of the rate is linear and 1 over T. Right? So as T gets bigger, the rate gets faster, right? And it's linear. Right? So if I were to then take this data and plot these rates as with 1 over T in the numerator, right, this is hotter as we go to the left, and the rate, right, and we should see a relationship that looks like this. So let me extend that the y-axis. And of course, where it intercepts is log of A. And this should make sense. So remember, the y-axis of this is where t is basically infinite, right? You have 1 over infinity, 1 over a very large number, so it's 0. Right, so the idea is that if the system has so much energy, right, it has infinite energy, right, it can do anything it wants, what's the fastest it can react? And the fact of the matter is that the fastest it can react is the amount of reaction opportunities that it has. It basically says that at infinite temperature, or very, very high temperature, then 100% of the CH3Br molecules have enough energy to react. So this entire term right here goes away, and you're just left with A. Right? So you're ultimately limited by the number of opportunities in your system. Okay, so that's the ultimate limit, right? The rate can't be any faster than the ability for the system to react. Right? How many collisions per second occur? As we'll see, for liquid reactions, so for liquid phase reactions, A is on the order of a vibrational frequency. And this tends to be on the order, that means A tends to be on the order of 10 to the 12 to 10 to the 15, if not more. Okay? So on average in liquid phase, 1 mole, just kind of normal standard state, A tends to be kind of on the order of 10 to the 10. All right? So that usually means on the order, that reactions occur basically once every femtosecond to picosecond, which is a common rate for these for most reactions. It's about a picosecond. This is a picosecond, so this is 1 picosecond, and this is 1 femtosecond. I mean, somewhere around the order of a pico to a femtosecond. Some are slower, of course, and if there's electrons, they're even faster. Electron transfer has an A on the order of 10 to 18. Right? So it just depends on the reaction. As we learned in the gas phase, A's tend to be a lot lower. Because, of course, there's not as many collisions in the gas phase. Okay. And so what we've done is just do a very kind of qualitative approach, right? We've done very empirical, right? We've come up with kind of a very generic concept of what it means for the energy for the system as it reacts. And we can do some experiments and we can monitor, we can figure out exactly how fast the kinetics by just monitoring how fast the products form as a function of temperature. Right? And the thing that I want to take home from this, the big take-home point, if you will, for this. How much time do I have? Oh, plenty of time. Great. The big take-home point. The equilibrium is determined by the energy difference or delta G between between the products and reactants. Kinetics don't care about delta G in this sense. Kinetics are determined by the energy difference between the initial state and the point of highest energy along the path, or along the reaction coordinate. Right? Typically, this is the transition state. So typically, E sub A is greater than 0 and defines what's called the rate limiting step. Right? It's the thing that slows everything down. The fact that the system has to get over this barrier in order to react. Right? So what we're measuring in kinetics, so in equilibrium we're measuring this energy difference, but in kinetics the one that matters is this one. The one between the trough and the peak. Okay? So very different measurement. But there's a problem. The problem is, all right, so it's, the nice thing about equilibrium is that we can measure reactants and products, no problem, right? We always have a mixture. So if we know that there's, if we make all just methanol and we have no bromine left after this reaction is left to complete, then we know it's delta G less than 0 because equilibrium is product. But if we have a mixture, then we know delta G is probably close to 0. But how do we measure E sub A? The fact of the matter is that we can't. Problem is, transition states are not detectable or isolatable. Let's say isolable. They exist only for a tiny fraction of a second, if at all. Right? So the transition state, despite the fact that we define it, right? We say there's a maximum of energy there. It probably looks like this. We have no proof of that. I mean, you can calculate it, but we can never measure this experimentally. And the reason why is that at equilibrium, a system requires, the system must satisfy two things. That the derivative of Gibbs energy with respect to the coordinate, right, the slope is 0. We call this a stationary state. And that the second derivative, the curvature, is greater than 0, which means that it's a minimum. Okay? So on this reaction coordinate, if we ignore this, just ignore the second derivative test and just do the first, then we say, okay, well, the system can be here. Well, that's where the derivative of the energy curve is 0, right? It's flat there. It can be here, but it can also be here, right? All 3 points satisfy this stationary state. But the problem is that the transition state has a negative curvature. So it's a maximum. And so it doesn't satisfy the minimum energy principle. So this state is not stable, right? And that, again, you can explain that by thinking about placing a ball here and then jiggling it just a little bit. And once you jiggle it, it's going to fall either way, right? There's no stability there. Meanwhile, if you jiggle a ball here or here, if I put the ball here, well, it's just going to roll back down towards the stationary state. But this one doesn't, right? You jiggle the ball at the transition state and it's going to fall into one of the wells, right? It's not going to stay in the same place. So a transition state is never isolatable. I think isolable is not a real word. Is it isolatable?
I like it, let's keep it.
I like isolable too, but I'm going to replace it.
Trademark it.
I think it actually is a real word. I'm just not sure it actually is that definition.
We can just gaslight people.
Yeah, okay.
It's real world, right?
Yeah, that's right. So we don't really have much luxury, but the nice thing is that with the Arrhenius equation, we can measure the energy indirectly, right? The rate is only dependent on the temperature, and, well, only dependent, ignoring ln A, on the temperature, which we can, of course, define, and the activation energy, right? So we can measure the fraction of, we can measure the kind of fractional characteristic of the molecules that get, right? We know, we can kind of measure how many molecules in our system have enough energy to get over this barrier because it's in the slope of the Arrhenius equation. The slope of this, again, so this is minus EA over R, gas constant. So we can measure energetic characteristics of it, but we can't actually observe the transition state. And so if you, we'll see this more often. It's interesting because lots of people have tried to look for the transition state. There's a Nobel Prize in the early 90s, it was maybe the late 90s, man named, well, now I can't think of his damn name now. He's Egyptian. Well, anyway, but he does these systems. For instance, where he dissociates I2. Okay, there's a really classic example of it. And I2 has in order to go from I2 to two iodines, there's a slight transition state. Right? And he does this laser spectroscopy on it, where he pumps the system full of energy so that it's above the transition state. Right? He pumps I2 full of energy so it's above this barrier, and then probes an atomic transition on the other side. Right? So he pumps it full of energy and then probes it on the product side, and looks at the formation of iodine atoms as a function of time. And what you find is that if you pump the energy up high enough, and you look at the transitions or the spectrum of iodine atom here, that the system oscillates between these two. So when you put the energy up here, the system sometimes is here, and sometimes it's here. And he can watch those oscillations in time. They occur very fast, right? They occur on the rate of the iodine bond frequency. The iodine bond vibrates at a specific frequency, and that tends to be on the order of about a couple tens of femtoseconds. It's very fast. But he can see oscillations where the system becomes an atom and then goes back to molecule, then comes back to atoms, goes back to molecule, right? So he can watch the system transit across the transition state. And the frequency at which that transiting occurs, that oscillation between I2 and 2I, the oscillation between those two, tells you something, the oscillation frequency tells you something about the height of this transition state. Right? So he can monitor the dynamics across the transition state and see the system oscillate between the products and the reactants, but he can't actually isolate the thing in the middle. Of course, the thing in the middle is just stretched I2, so it's not really a great example. Right? It's just kind of I2 kind of on the edges. Right, so the system kind of oscillates between atomic and molecular, back and forth, back and forth, back and forth, and you can see that. So you know there's a transition state there, because if it wasn't, if it was flat, for instance, if the reaction coordinate looked like this, so again the assumption is that, so for I2 it looks like this. This is I2 and this is 2I, and he pumps the system up. So he does a pump here to way above the transition state, and then does a probe here. So this is where you get your spectrum. And what he sees is, again, when he puts the system up at this energy, if you look at the time versus concentration of I2 at this probe, you find that it oscillates back and forth and slowly decreases as it converts, like this. So these oscillations are dependent on this barrier right here. But maybe, for instance, this reaction looks like this, right? If it looked like this, well, then this would never be stable anyway, because it's just everything here is going to go back, right? So if this were the case, if you pump the system up here and probe here with your atomic spectrometer, all of these systems are just going to go right back into here, right? They're just going to roll down the hill, right? So the spectrum of this will be high at first, and then as you pump it, it decreases, and then it comes back again, right? Because you remove the I2s, they start to make atoms, so the concentration drops, and then it's going to rise back up again because it's going to come back down. Right? In fact, let me actually make this a little better. It actually looks like this. It actually doesn't decay that much because it's at equilibrium. It's like that oscillation. Likewise, there's one more case, which is where, I'm sorry, this is the coordinate where the system doesn't have any transition state at all. Imagine that this were exothermic instead. Right? And you did the same process. You pump the system up to some high energy and then probe here. Then what would happen is that you have a high initial concentration of I2, and then when you pump it, it's just all going to come right. It's all going to roll down this hill, right? So it's just going to look like that. Right? No oscillation occurs, right? So the fact that there's an oscillation implies that there's some slope that going backwards and going forwards, there's a rate limiting step, and they compete, right? Because if the system's here, it can go this way, but if the system's here, it can also go this way, right? So these two are occurring simultaneously, and he's able to track it fast enough. His lasers and his spectrometer is fast enough that he can watch it oscillate in time, right? And that proves that there's this transition state in between. It has to, because the only other possibilities would lead to non-oscillatory spectra or time dependence, right? They're just going to roll down the hills otherwise, right? So the transition state implies this oscillatory behavior, right? So if you can detect this oscillation, you can't ever observe the thing in the middle. You can't pull that out. Because of its presence energetically, you can watch it oscillate between. You can watch the forward reaction compete with the reverse reaction. Right? So he won a Nobel Prize for this. Ahmed Zewail, that's his name. Zewail. I think he's retired now, or dead. One of the two. I can't remember. I don't think he's dead. I think he's just retired. Yeah, I forget, but I think he's dead. What time is it? Okay, we got 15 minutes. Okay, great. So we won't go into these details about iodine so much, but the idea is again, the activation energy defines everything about kinetics. We can't ever measure a transition state, but its presence is always indirectly known, right? In some ways, the activation energy is always measured indirectly and somehow defines the entire system, right? The entire kinetics of any molecular system is defined by the activation energy, its presence or its non-presence. Right? And the indirect measurements that we do of the system will tell us something about the transition state. Right? We can do Arrhenius. Right? Arrhenius will tell us the transition state has the slope, right? Has the activation energy for the slope. Or if we do things in time, we can actually watch things oscillate. Okay. Before we finish, I just want to derive one thing.
Is it the concentration versus the energy for the orange one?
This one?
No. What color is that? The red one.
This one.
Yeah.
Yeah, concentration versus time.
Okay. Oh, that's time.
Yeah, measuring these in time.
I thought it was positivity.
No, it's time.
Doing that too.
It's in time. So, yeah.
Today's time.
So if you're like, yeah, the more amps you put into it.
All right. So what I want to do really quickly is show you that equilibrium is just a kinetic property. Chemical equilibrium is just kinetics. Right? This is a really, really simple derivation. Okay? I'm going to erase some things in this plot here and use it again. I'll say no. No, there's no need to. But I just want to have it here, just so I can define a couple of numbers.
So we don't need to redraw?
No, we need
No,
to
you-
redraw it.
Well, you can just quickly sketch it, okay?
That's it.
You don't really need all of it. I'll show you what you need. All I need to measure is, I want to define this. This is the activation energy for the forward reaction. We'll call it EA1. And that this is the activation energy for the reverse reaction, EA2. Okay? Right, so remember this, in a system we can go backwards or forwards, right? The microscopic reversibility tells us that it's just as easy to go backwards as it is forwards. Okay, so let's think about, let's just write this in terms of CH3Br and CH3OH. We don't care about the ions so much. All right, and so let's look at the process of CH3Br to CH3OH. We can write that the change in the concentration of CH3Br with respect to time is equal to the reaction rate, the forward reaction rate, times the concentration of CH3Br. Right? It's just a rate law. And the reverse reaction, so this is forward. And I write it in a different way. Reverse, which is CH3OH to CH3Br. The rate of change of CH3OH, right, the depletion of the products to form reactants with respect to time is the reverse rate times the concentration of CH3OH. Okay, and we can write, let me make sure the colors are consistent. We can write Kr forward, the forward rate, which we'll call K1, as A e to the minus EA1 over RT. And of course, the reverse rate we can define the same way, but with the reverse activation energy. So K2, which is Kr reverse, or let's say K minus 1, that's the typical K minus 1, is A e to the minus EA sub 2 over RT. Right, so we have a rate going this way with this activation energy and a rate going this way with that activation. So the total reaction, so we can say that the total rate of depletion of CH3Br, our reactants, is going to be, I missed a sign here. Sorry, I missed a sign. These have negative signs. I apologize. Negative signs. Of course, as CH3Br reacts, the concentration gets lower, so this has to be a negative sign. So it's negative K1A plus K minus 1. Sorry, I'm not using A. Sorry, CH3Br. Let me rewrite this. Sorry, I apologize. My notes are slightly different. CH3Br. So we depleted at the rate, the forward rate, where we're depleting CH3Br at the forward rate, which is the minus sign. And then when the reverse reaction occurs, we add to CH3Br. So we plus it, K minus 1 times the CH3OH. Right? We're just adding the two laws together. Okay? So the rate of depletion of reactants is modulated by its kinetic rate going forward, and then the reformation of itself by the reverse rate, reverse reaction. Okay, and so let's assume that the initial concentration of Br at T equals 0 is just CH3Br naught, just a number, right? That's the initial concentration. And that the initial concentration of methanol is 0. Okay, so we just have reactants. Oops. So that means then that the rate of change for the depletion of our reactants, CH3Br, dt, is minus K1 CH3Br plus K minus 1 CH3OH. Okay, but every mole of CH3Br that reacts forms a mole of CH3OH. So the CH3OH's concentration as a function of time is just the initial concentration of CH3Br minus the amount that hasn't reacted yet. Right? If the entire system reacts to completion, then you'll have the same concentration of CH3OH as you had initially for CH3Br. Okay, so we can relate to them, right? Because they're the only two things in the system. Right? So as you remove one, you make the other. So they're inversely related to each other. So we can simplify this, and this says that the derivative, the change or the slope of the concentration of our products, our reactants as a function of time, is equal to minus K1 plus K minus 1 times the concentration of our reactants. plus an extra term, K minus 1 times the initial concentration. Okay. All right, so I'm just making some substitutions. Now what I can do is multiply both sides and separate the variables and put T on one side and CH3Br on the other side. So that's kind of a big nasty thing, but so it's going to be K1 plus K minus 1 CH3Br equals, I missed a minus sign here. Sorry, there should be a minus sign there. Yeah. Equals K minus 1 CH3Br naught times dt. All right. Multiply both sides by dt and then got rid of the CH3Br, the concentration of bromine, methyl bromide onto the other side. All right, and we can integrate both sides. So we'll integrate from 0 to t. And on this side, we'll integrate from CH3Br initial to CH3Br, right? The concentration at some given time t. Okay. And when you integrate these, you get a nice equation that says that the concentration of bromine as a function of t, right? Here we're integrating something with respect to the bromine concentration, so this will end up being something in terms of the bromine concentration. And here we're integrating with respect to time, so there's going to be some time here. So we're going to have a function of concentration that's equal to time is equal to K1 plus K minus 1 plus K1 e to the minus K1 plus K minus 1 t over K1 plus K minus 1 times the initial concentration. Right? This is really powerful. So the function, the concentration of our reactants as a function of time is just dependent on time and the rate constants, right? The activation energies, right? Times our initial concentration of bromine, right? This is just a factor we can even divide both sides by it just to get rid of it. Right? And there you can see that the change in the bromine concentration is just a function of T, right? It's an exponent in terms of T, and there's some constants. Right? You can almost write this as, it's just a number plus another number times an exponent. Right? So it's just a number plus e to the minus t. Okay. So if I were to plot it, we know that it would look like this. It starts at some initial concentration and then decreases over time like this. Right? That's all it looks like. It's just an exponential. Okay, so let's let t go to infinity, right? We're going to equilibrate the system, right? We're going to wait forever and reach equilibrium. Okay, so that means then that t goes to infinity. T goes to infinity here, so this becomes 0. Right, because you have e to the minus infinity, that's 0, right, goes to 0. So that means then that the rate, that the concentration of Br at times t equals infinity, which we'll call equilibrium. So the equilibrium concentration of bromine, or methyl bromide, is equal to the reverse rate times the initial concentration of bromine divided by the sum of the rates and then we know that the concentration of methanol at equilibrium is going to be the initial concentration of methyl bromide minus the equilibrium concentration of methyl bromide. Right, we've reacted some methyl bromide, it's become methanol, right? So that's the natural way to assign these. Which means that CH3OHEQ is equal to the forward rate times the initial concentration of bromine divided by the sum of the rates. Okay, so we have an equation for the concentration of methanol at equilibrium, one for the concentration of bromine at equilibrium. Now let's divide. Let's calculate the equilibrium constant. KEQ is going to be CH3OH EQ divided by CH3Br EQ. And we can just plug in those formulas. We have K1 times the initial concentration of CH3Br divided by the sum of the rates divided by the reverse rate times the initial concentration of bromide times plus the sum of the rates. Look how all these things cancel out. This goes away, this goes away, this goes away, this goes away. And you're left with the ratio of the forward rate minus the reverse rate. So all equilibrium is I'm going to do double, all equilibrium truly, I don't want to say is. All equilibrium can be reduced to a measurement of competing rates. So if the forward activation energy is greater than the reverse activation energy, like it is, or not like it is here, this is the opposite case, that means then that the reverse rate is faster than the forward rate, right? Because the activation energy for the forward is larger, which means that K is less than 1, or less than 1. It's reactant phase. Meanwhile, if EA2, the reverse rate, or the reverse barrier, is larger than the forward barrier, which is the case here, the forward rate is faster than the reverse rate. And so KEQ, the equilibrium constant, is greater than 1. Okay? So the fact that we've distinguished between equilibrium and kinetics is entirely arbitrary. They refer to the exact same thing. All equilibrium truly is that you have two competing rates, a forward one and a reverse one, and if you wait forever, eventually one's going to win out, and that determines your equilibrium constant. Right? So in fact, to measure equilibrium properties, we don't even need to think about delta G. All we have to care about are the relative differences in the activation energies. Of course, if we notice, that's just circular logic, because in fact, if we look here, again, this difference right here is delta G. So EA1 plus delta G is equal to EA2, right? Right? The only difference between this activation and this activation energy is just the energy difference between the products, right? So that's all I'm saying, right? So it doesn't really matter which way you look at it. The fact of the matter is if you have two minima that are connected by an activation energy, that all the kinetics, all they are is just equilibrium competition, right? Competition between the two rates, and whichever one is faster, you end up getting more of the resultant product from that ring. And so kinetics and equilibrium are precisely the same concept. So we can measure equilibrium either way. Sometimes it's easier to do it by measuring equilibrium concentrations, and sometimes it's easier to do kinetics. Right? And so we're going to focus more on the kinetics part here. But anyway, they're exactly the same concept. Okay, I'm a little late. I'm sorry, guys. We'll come back to this topic of kinetics on Thursday. We'll look at things a little more microscopically. We'll talk about collisions.
It's a long time since a whole equation on one page. It's been 2 years.
USA won, by the way.
Oh, fantastic. We play Netherlands on Saturday, I think.